Good afternoon, guys, and welcome to my online session provided by SPE Universidad Nacional de Ingeniería. I hope I said it right. I would like to express my gratitude for giving me such an opportunity to be with you, and I would like to show my total support for you guys in Peru. You guys have done marvelous job so far, and I expect a lot from you. So congratulations. During this session, we would get introduced to the material balance equation and how to calculate the hydrocarbon initially in place manually and by using MBal software, and how to predict for the future performance. I will provide you with my email in case if you have any inquiries about this session. You are welcome to send me anything at any time, and I will reply as soon as possible. So good luck, everyone, and I hope you enjoy it. Thank you. So this is my email in case if you are interested to know more about the reservoir engineering in general, or the MBal software, or the material balance equations. Any questions, I would reply as soon as possible to each one of you. This is my email, mohamed.h.yassin@hotmail.com. Anyway, our agenda for today is that we would talk about the types of reservoirs we have, the kind of reservoir fluids, and the driving mechanisms for all of the reservoirs, whether it's saturated or undersaturated reservoirs, and we would know the difference between both of them. Second thing is that we would know how to calculate, how to manually calculate the hydrocarbon initially in place, whether it's oil or gas, by using the material balance equation based on the production history data or the actual field data that we have. The last thing that is getting introduced to MBal software applications and knowing how to use it to know the driving mechanisms, to know the type of reservoirs that we have, to predict for the future performance of the oil using water injection or gas injection cases. It's nearly a very interesting software to use and a very powerful tool to use in reservoir engineering in general. So we have three types of reservoir fluids, as you all know. The first thing is the water reservoirs. These reservoirs are only used if you are going to inject water into your main oil or main gas reservoirs. They are not very important to us, and I don't guess we drill into water reservoirs unless we want to inject water. The second thing is that we have gas reservoirs with two types. The one with the bottom water drive reservoirs, and the second thing is without the bottom water drive reservoirs. The last thing that we would talk closely about is the oil reservoirs. Actually, the oil reservoirs are divided into two main categories. The first one is the undersaturated reservoirs, and the second one is the saturated reservoirs, oil reservoirs. The main difference here is that the undersaturated reservoirs are the reservoirs where the pressure or the reservoir pressure is greater than the bubble point pressure. So you don't have any free gas in this layer or this formation. You only have gas dissolved in solution, and there are two types of these reservoirs, the one with the bottom water drive and the one without bottom water drive. The second category, as we said, is the saturated oil reservoirs, where the pressure is less than or equal the bubble point pressure. So we would see some free gas, but if the free gas isn't enough to form a gas cap, this is called solution gas drive or depletion reservoirs, or it is called gas in solution drive reservoirs. If the free gas is great enough or high enough to cause a gas cap, this is a gas cap drive reservoirs. If we have bottom water drive reservoirs, we would see some free gas, but the main driving mechanism here is the bottom water drive. And the combination drive reservoirs are the reservoirs where you find all of these things together. You find the free gas, you find the bottom water, you find everything about the saturated oil reservoirs. So, there are three main methods to calculate the original hydrocarbon in place. HIIP is the abbreviation for hydrocarbon initially in place. We have the volumetric method, and we will talk about it briefly. We have the material balance equation, and this is our main concern during this online webinar. And the last thing is the decline curve analysis, but we wouldn't talk about it very much. The volumetric method, in order to calculate the hydrocarbon initially in place, you should have an isobach map where you know the area of it, when you know the thickness or the net thickness of the formations that you have, in order to calculate the hydrocarbon initially in place by using the volumetric method. This method is probably used by geologists or geophysicists in order to calculate this hydrocarbon in place. We have two equations here. The first one is N equal 70758 multiply H, where H is the net thickness, as we said. A is the area of the reservoir in acres. This phi is the porosity. Actually, it is the average porosity for all the reservoir. Multiply 1 minus the initial saturation of oil divided by beta OI. It is the initial oil formation volume factor when we start producing from the reservoir, or before production. G is the same equation, but N is for the original oil in place and G is for the initial gas in place. It is a very simple and very general equation to calculate the hydrocarbon in place, but it isn't very accurate, because you may have some accuracy, or you may have some errors in calculating the area of the reservoirs using the map. You may have some errors in the in the net thickness of the formation. All of these things leads to an error in the calculations, so it isn't very accurate, but it gives you an approximate estimate for the original oil in place or the initial gas in place. That's why geologists and the petroleum engineers are always in conflict, because those geologists have a certain number for the initial oil in place, and those reservoir engineering have another number, so they keep conflicting with each other. So anyway, the material balance equation is nearly the most accurate method to calculate the initial hydrocarbon in place. But why is that? Actually, because the material balance equation depends on the actual data or the production history that you have. It depends on the net produced oil, on the produced oil during the production of the well. It depends on the oil formation volume factor, gas formation volume factor, the RS, the initial RS, the RP. All of these things are, calculated in order to give you the most accurate approximation for the hydrocarbon initially in place. The reason why I gave you, talking about the saturated reservoirs, I have given you the general formula for the combination reservoirs that we were talking about. The reason why I gave you the general formula of the combination only is that if you understand it very well, you would be enabled to calculate the depletion reservoirs, the gas cap reservoirs, the water driving mechanism reservoirs. All of these things could be manually calculated by using this general formula, and I will teach you how later on. Okay, just imagine that we have a reservoir with a gas cap, with oil in place, and with water drive mechanism, the combination reservoirs that we have talked about before. If we want to know the volume of the gas that we have, we would multiply the initial gas in place, multiply beta gi, or the initial gas formation volume factor. This would give you the volume of the gas initially in place at the reservoir condition. The same thing for the oil in place. We'll multiply it by the beta O initial. This will give you the volume of the oil at the reservoir condition. And the last thing is WE, is the water influx or the water drive mechanism for the combination reservoir. Imagine that, and we have the initial pressure of the reservoir P initial, PI or P initial. After a time, delta T, you would find that there was some free gas that evolved from the reservoir due to the depletion of the well. And the second thing, that you would find the original oil in place minus some part, which is the NP or the produced oil that you have already produced. And the last thing is the water that you have already produced during the depletion phase. So how to calculate all of these things in order to get the original oil in place? Let's keep in mind that M, we're going to talk about the term M. M is the ratio between the gas volume at the reservoir condition, or the initial gas in place at the reservoir condition, divided by the initial oil in place at the reservoir condition. Let's talk about the main concept of the material balance equation. Is that all the volume at all the times are the same. So if we look here, we'll find that N beta OI plus G beta GI, supposed to say plus WE, but we changed it in at the other side. We'll find that's equal to N minus NB. This is the initial oil in place minus the produced oil that you have already produced, multiply beta O in order to get the volume of the oil remained at the reservoir condition, plus WE or the water influx minus WP is the produced water during the depletion phase, multiply beta W in order to know in order to get the volume of the remained water at the reservoir condition. Actually, WB here it doesn't need to be multiplied by beta W, because WE is already at the reservoir condition. This is the volume of the water at the reservoir condition. Okay, we would find these remained oil and these remained water, besides some free gas that has already evolved during the depletion. Okay, but what is the free gas that has already evolved that we are talking about? The free gas is some of the gas in place, the initial gas in place that we have, plus NRSI is the gas in solution that is remained, plus N minus NPRS is the free gas that is evolved above the oil at the reservoir condition, minus NPRB is the gas already produced. Let's say it again, because I guess you are probably confused. This is the original gas in place that we have, plus the gas in solution initially found at the reservoir, minus the gas in solution remained after production, minus the gas produced already during the depletion phase. Is that clear? Great. So if we arrange the this equation, we said that m equal g beta gi over n beta oi. Okay, so we can substitute for the g for m beta gi over n beta oi, right? Or simply, if we have g beta gi, we can substitute for this term with m n beta oi, as written here, equal the same thing, n minus np multiply beta o. This is the oil that is remained at the reservoir condition, plus we minus wp beta w. This is the water that is remained at the reservoir condition, plus all of these terms are the gas or the free gas at the reservoir condition. And as we said, G is the initial gas in place again, NRSI is the initial gas in solution, minus N minus NB all multiply RS is the gas in solution that is remained at the reservoir condition. N minus NP RP is the gas produced already at the production phase or the depletion phase. If we arrange all of these equations together, we will get that N equal all of these terms that you are looking at. I know that it may seem a very long equation, but if you understand the concept of how to derive it, it would be very easy. And that's why I talked about the combination reservoir specifically. Because imagine that we have a depletion reservoir. We said the depletion reservoir is a reservoir that have free gas but not a gas cap reservoir and not a water drive. So if we want to calculate the depletion reservoirs using this general equation, the first thing we would cancel this term. All of this term would be cancelled. Why? Because there is no water in this reservoir, right? And the second thing, this term would also be cancelled. The reason why, because we don't have a free gas cap reservoir. This is the equation of the depletion drive reservoirs. It's very simple. It can be derived from the general combination reservoir equation. Okay, let's imagine that we have the gas cap reservoirs. The gas cap reservoirs doesn't have water drive in it, right? So this term of water should be eliminated. But this term will still exist. Why? Because during the gas cap reservoirs we have the free gas and we have the M term. So this would be all the equation. This will be all the equation of the gas cap reservoirs. Okay, talking about the water reservoirs, the water drive reservoirs actually. The water drive reservoirs have this term, so it won't be eliminated, but we will eliminate this term. Why? Because there is some free gas in the water drive reservoirs, but it doesn't form a gas cap. That's why we will eliminate this term, and this is the equation for the water drive reservoirs. Are we fine with that? Great. Talking about the general combination equation for the saturated reservoir, and all of these equations that seems very confusing actually. This is the same equation but we rearranged this equation in order to have a straight line equation. All of this term NP beta O plus RP minus RS beta G plus WP beta W, we could have all of this term and substitute it by F. Call this term F. Okay? F is an abbreviation for flowing. So let the N, or the initial oil in place, remains at it is, and let's say that this term and this term, without the N, we took the N as a common factor, okay? And these two terms, this term we renamed it EO, or the expansion of oil, and this term we would not this term, I mean this term, we would rename it as EG. EG is the expansion of gas, as here. So we took N as a common factor, and we have EO, or the expansion of oil, equal beta O minus beta O initial plus RSI minus RS beta G, plus all of these terms, M beta OI over beta GI multiply EG, or the expansion of gas, which is equal to beta G minus beta G initial, plus the water influx that we have. Okay, we can sorry, it's a little bit confusing. Okay, we can take this term, we can divide this equation by this term for both sides. We will get F divided by this term equal N plus the water influx divided by this term, and that is the equation that we would get the straight line from it. This is the Y. Okay, let's remind ourselves by the straight line equation. Y equal mx plus c. Excuse me for my bad writing, my bad handwriting. Okay, let's say that the Y is this, the left hand side, F over E node plus M beta OI over beta GI multiply EG, and this term is the constant, or C, and this term N is the slope of the equation. We would have a X. Actually, the X that we are talking about is equal 1. If we remind ourselves by the trigonometric equations, tan theta, when it's equal 1, so theta equal 45 degrees. So if we apply these equations, we would find out that the tan theta here is equal 1, so theta is equal 45. We will have a straight line with the slope n, and it should be making 45 with the 45 degrees with the horizontal line. Okay, are we clear? Great. So talking about this is the saturated reservoirs. Talking about the undersaturated reservoirs, it is the same concept. It is the same concept for the saturated reservoir, but there is a little bit difference between them, because when the reservoir is undersaturated, or the reservoir pressure is greater than the bubble point pressure, we would consider into account the WC, the WC and the CF. What is the WC and the CF? WC is the water compressibility, and CF is the formation compressibility. Actually, there is another term called CO. CO is the oil compressibility, where it is equal to beta O minus beta OI over beta OI, or the initial oil formation volume factor, multiply delta B. And you should know, and you should pay attention to this information. In the CO equation, delta B is the pressure, or the current pressure, minus PI, the initial pressure. Again, in the oil compressibility equation, delta P term is for the current pressure P minus P initial, or the initial pressure. But in the N equation here, delta B is for P initial minus P, the current pressure. You know the difference? In CO, it is P minus P initial. In N equation, or the original oil in place equation, it is PI, or the initial pressure, minus the P. Okay? There's only one term regarding the fact that there is a derivation for this equation. We wouldn't talk about it very much because it's very long and it would take 3 or 4 hours to understand it. It's not very hard, but it would take a long time. So N equal NP, the produced oil, multiply beta O, the oil formation volume factor at this pressure, divided by beta O initial, the initial oil formation volume factor, multiply CE. What is CE? CE is the effective compressibility for the reservoir. CE equal CO, the oil compressibility, multiply SO, it's a saturation of oil, or oil saturation, plus CW, water compressibility, multiply SW, the water compressibility at this pressure, plus CF, as we said, it is the formation compressibility, divided by 1 minus SW, or the water saturation. This is the equation for the CE, or the effective compressibility that we have. Okay. It also have a proof, but it is very long, so we wouldn't talk about it much because we are mainly concerned here by using software, MBal software. And I don't guess you don't know about these things. It's very easy. If you have the basics of the applied reservoir, I guess you would know that better than me, of course. So as we said, in undersaturated reservoirs, there is we have to take into consideration the CW and the CF and the CO, the oil, water, and formation compressibility into account, because it acts like the main driving mechanisms for the undersaturated reservoirs, unless there is, of course, a bottom water drive that will support the oil to flow from the formation up to the surface. This term, we would call it F, or the flowing term. And of course, as we said, this term is compensated for the EO, or the expansion of oil. So we would get a straight line where F is the Y, N is the M or the slope, and E node is the X. And there is no constant, there is no C. That's why it will start from the origin point. Are we clear? Okay, welcome back again, and the first thing I would like to say is that I'm sorry for the mistakes that I have done in the first presentation. The second thing that this is where you will learn how to use the MBal software. MBal software is a very friendly user software that enables you to deal with a very simple panels. You don't need even an instructor to teach you how to do it. But anyway, if you open MBal software, you would have the tool panel with different options like material balance, reservoir allocation, Monte Carlo, decline curve analysis, and so on. We will talk about each one of them separately. The material balance tool is the main concern, where you would calculate the initial gas in place or the initial oil in place and predict for the future performance if you want to make a gas injection or water injection, and so on. The reservoir allocation tool is a tool which improves the allocation by allowing the user to enter IBRs for each layer and calculate the allocations by taking the rate of depletion into account as well. Crossflow is also accounted for in this model, and as well as different start or finish times for the well. Impurities are also tracked and can provide an effective measure of the quality of the underlying assumptions. This is in the case where few data is available. The third tool is the Monte Carlo, where you can calculate the P10, P50, P90 for the initial oil in place or the initial gas in place. In other words, the proven, the possible, and the probable reservoirs that we have. Decline curve analysis is where you calculate the volumetric the volumetrics of the reservoir or the hydrocarbon initially in place by using the decline curve analysis. 1D model is that if you have a water injection case, the 1D model of the Bakr model will enable you to do it, but it has a limitation because it's only for the the cuboid reservoir. If you have a circular reservoir, it won't help you very much. We have the multi-layer tool. The multi-layer tool is the relative permeability averaging for different layers, where it can be done using this tool based on a variety of methods like stills, for instance. Their relative permeability can be used in MBal or the Bakr lever tool or the 1D model, as we said before, for further analysis. The gas type reservoir curves, I'm not really an expert at that, so I won't talk about it. Okay, we will choose the material balance equation tool. Before getting started, I would like to introduce you to the units tool, where you can input all of these variables in oil field units or Norwegian units, Canadian, German, French, and so on. This is also for the output. If you want, for example, to input in oil fields, input the data in oil fields and to have the output data in Norwegian fields, for example, this will give you all the units that you have. What if you want the oil field to be the input data and the oil field units to be the output data, but you want to change something? For example, if you want to, if you know the decline curve analysis per month, you will click here and choose one per month or one per year and so on, without changing the rest of the oil fields, and then click OK. It's very simple and it's very easy. We don't want to change anything here, so we would choose cancel. Okay, as we said, MBal is a very friendly software. We can use it. We could follow a sequence from left to right and from top to bottom in order to get what we want. The first thing that we will press is the options panel. It will get you the company, the user information like the company, the fields, the location, and the platform if you are working on a platform, and the analyst with the reference time. Don't look about it. If you want to have any comments, like if you write SPE for example and you want to have a date stamp, you click here. It will give you the time and the date that SPE was written. Okay, it's very simple, and I guess for now on it's useless. Anyway, the reservoir fluid that we have 4 kinds of reservoir fluids: the oil reservoirs, the gas reservoirs. Actually, the gas reservoirs is named for the dry gas reservoirs. The retrograde condensate reservoirs, MBal uses the retrograde condensate black oil model. These models take into account liquid dropout in the reservoir at different pressures and temperatures. So there is a difference between the gas and the retrograde condensate. So what is the general reservoir fluid? This option allows the tank to be treated as an oil leg with a gas cap containing a condensate rather than dry gas. Or in other words, a tank can be treated as an oil tank with an initial condensate gas cap, or a condensate tank with an initial oil leg. This means that the user can enter a full black oil description of the oil and a full black oil description for the gas condensate. This allows modeling of solution gas bubbling out of the oil in the tank, as well as the liquid dropout in the tank from the gas. It's vice versa. We will choose oil because the example we have is the oil reservoir fluid. The second thing is that the tank model is whether it's a single tank or multiple tanks. Don't get confused with the term tank here, because tank here means reservoir, not the storage tanks that we have on the surface. MBal treats tank as it treats reservoir as a tank. It is not the storage tanks on the surface. Okay, so we would choose here a single tank because we only have one reservoir in the example. You have Bvt Model, 2 options. The first thing is the simple Bvt model, where the Bvt properties are fixed at a fixed depth. If you have, for example, a reservoir with a thickness of 30 or 40 feet, you would have all the Bvt properties the same at a constant pressure for all the depths. But the variable Bvt model, it will give you at the same pressure, it will give you different Bvt properties at different depths. So the variable here is the depth. If you change the depth, you would get a variable Bvt, or if you change the depth, you will have the same Bvt in the sample Bvt. Okay. The production history that we have here is by tank or by well. If you have all the production history from the reservoir itself, you would input the data by tank. If you have each well separately, you would enter it by well. Okay. The compositional model, you have 2 more options besides being none. The first one is the tracking or compositional tracking, and the second one is the fully compositional. The difference between these 2 options, the compositional tracking is simply tracking the compositions by flashing the fluid at the different resulting pressures during a forecast, considering of course its equation of state. But the full compositional option, it will calculate all the Bvt properties using the equation of state, as well as tracking the compositions at different resulting pressures. Okay, we will keep it simple and we will choose none, and then we would choose done. Okay, the second option is the Bvt, where we will enter our fluid properties Bvt. If you get confused during using this software, it's very easy, but if you get confused, the formation gas oil ratio, is it RS, the solution gas oil ratio, or the gas oil ratio as we all know, whether it's at the bubble point pressure or the reservoir pressure or at the standard condition pressure? You don't know, right? You would press help and it would give you all the information that you need. For example, the formation gas oil ratio, if you read it on your own, you would think that it is the gas oil ratio that we know. Actually, it's not. It is the solution gas oil ratio, or the RS, at the bubble point pressure. It won't include any free gas production. So the formation gas oil ratio and so on. The formation gas oil ratio here is the RS at the bubble point pressure. For example, if we have the formation gas oil ratio, let's enter it as 500. Okay, this is an example actually. The oil gravity, let's enter it as the 39 ABI. I know it's a huge number, but it's okay. It's within the range. And the oil gravity here is at the standard conditions. How did I know that? From the help button, as we said, the oil gravity is the gravity of the condensate at standard conditions, and so on. The gas gravity, let's enter it as specific gravity, 0.798. The water salinity, let's say that it's 100,000 ppm, part per millions. And let's assume that there is no H2S, there is no CO2, there is no N2. Okay, after inputting the parameters, we want to match the data that we have from the production facility. We want to match it with the data obtained from the Bvt laboratories. How could we match both of them? We have the match button here. Please click on it. It will give you about I don't know, maybe 100 or less, I'm sorry, maybe 20 or less tables for the Bvt data obtained from the laboratory. Let's say that the temperature of the reservoir is 250 degrees Fahrenheit, and the bubble point pressure is 2200 psig. Let's enter the pressure as we said, 2200 psig. The gas oil ratio here is again the RS, the solution gas oil ratio, or the RS. Okay, let's enter it as 500. Oil formation volume factor 1.32. Oil viscosity is 0.4. Of course, if you have all the data from the Bvt laboratories, you would enter it here. The main conflict here is that the MBal manual says that you have to match the data that you have from production with these data, but these data should be obtained from the CCE experiment, or the constant composition experiment. Actually, here in Egypt, most of the companies, or nearly all the companies, are using the adjusted Bvt data. That's a point of conflict, and it won't be very different in results. It won't have a huge difference in results actually. So anyway, if this is at the constant temperature. If you have made Bvt data with several temperatures, with different temperatures, you would choose here table 2 and enter the temperature, say at 200 and so on. I'm sorry, at 200 and so on. If you have this, if you don't, just enter the Bvt data at the given temperature, as most of the Bvt laboratories do. So whenever you do this, click match. I'm sorry, I forgot to tell you something. If you want the pressure to be in psi-G, to be in psi-A or so on, you can change it from here. The same for the gas-oil ratio, the same for the oil formation volume factor, and so on. Okay? So whenever you do this, click match. Once you click match, well, you have several options: the bubble point, the gas-oil ratio, the oil formation volume factor, and the oil viscosity. You only have to take on the things that you are pretty sure of it. In most of the cases, we choose bubble point pressure only because we are pretty sure of it. But we would give it a try, and we will choose all of these things during this session. Okay? Once you have taken the things that you are sure of it, you click on match all. Okay? And then click on calculate. Once you click calculate, you should choose match parameters. Okay, what is this? In the match parameters panel, you have the bubble point pressure, you have the RS, you have the beta O. Each one has all of the correlations that is mostly used: Glasso, standing, Glasseter, Biggs, Petrosky, and Marhoon. We should pay attention to the standard deviation in each one of them. For example, in the bubble point, the standard deviation in is 1.2 multiply 10 power negative 11. Here is 4.36 multiply 10 power negative 11. Here is 8. Here is 1. Here is 1.59. Here is 9.09 multiply 10 power negative 12. So what is the least standard deviation among all of these correlations? Actually, it is in Marhoon. So in Marhoon is nearly the best match for calculating the bubble point pressure from the actual data that we already had. In the solution gas-oil ratio, we would find that I guess standing is the least equation that has the least standard deviation. So here is the standing, and at the oil formation volume factor, we will get Glasso, standing, Glasseter, Big. I guess we will have the yes, we would have Petrosky. So we have different correlations to calculate each one of these variables. What should we do? Should we choose standing or El Marhoon or Petrosky? What did we say here? Yes, should we use standing or Petrosky? Actually, we would choose it standing. Why? Because standing gives two matches in bubble point pressure and solution gas-oil ratio, and the Petrosky give only one oil formation volume factor matching, right? But to be clear, if you have an equation that gives matching in each one of them, like if you have at bubble point, if you have Glasso is the best one at solution gas-oil ratio, if you have standing at oil formation volume factor, if you have Petrosky, then you would have different equations. What should I do then? You would require to choose the equation that gives you the bubble point pressure, the least standard deviation at the bubble point pressure. This is the most accurate one. But here we already have two matches: standing equation for the bubble point pressure and the solution gas-oil ratio. Only Petrosky is the least standard deviation equation at oil formation volume factor. So we would choose standing for the BP, RS, and beta O. Okay, when we look at the viscosity of oil, viscosity of gas, and the beta G, we will see that the same things but with different correlations. We'll see that P-etal is the least. Yes, P-etal is the least standard deviation. So we will choose P-etal for the viscosity of oil, the viscosity of gas, and the beta G, and we will choose the standing for the bubble point, solution gas oil ratio, and formation volume factor. Once we have decided which equation we would choose, we press on done, and then done, again done. You will see that the use matching will appear and disappear. This means that you already matched the data you have, and we will choose standing here as we said for PP, RS, beta O, and we will select P-etal for oil viscosity, and then we click on done. Great. Once we have finished the Bvt data, there is also a tool for Bvt if you want to calculate the Bvt data. This is only for trial. If you have a temperature, say from 150 degree Fahrenheit to 200 degree Fahrenheit, and you want to have the steps, each 10 only 10 steps between 50 or 150 and 200, you'll say that each 5 degree increase in temperature you would have as the pressures. Also the pressures from 2500 to 3500, and the steps is 10, and you use calculate and then calculate. It will gives you an approximated Bvt properties for all the properties you would ask using the data you have already entered, from 150 temperature, 155, 160, 175, and so on. Okay, it's not very important, but if you want to automatically calculate the Bvt data using the correlations that you define, it's not very hard. So anyway, when after we finish the Bvt data, we press on input and then tank data. Actually, the tank data, you have what type of tank type is whether the reservoir is oil or water. We would choose that the reservoir be water. Okay, the name of the tank is the same name that appears here, tank 01. Let's say that its name is SPE. Okay, the temperature of the reservoir, once again I remind you that if you don't know what kind of temperature does he need, or what kind of temperature does this program need, you can check the help button. Anyway, the temperature here is the reservoir temperature. So the temperature is I guess we said 250, right? The initial pressure 2200 psig. The porosity is 0.23. Connect water saturation 0.15. At water compressibility, you have two options. Either to leave it at this, use core means use correlation. The program will use the correlation to automatically calculate the water compressibility. Or either you could give a certain value to the software, so it doesn't matter. We will leave it just like that as user correlation. Okay. Initial gas cap. Suppose that you don't know about the reservoir that you are dealing with, and of course you don't know whether it has a gas cap or not, whether it has a water drive or not. So we will assume that there is no gas cap at the reservoir that we have. We will say that 0 means there's no initial gas cap. Okay, The original oil in place, you don't even know the original oil in place, right? We will assume that it's, say, 150 mmSTP. Maybe this number is right, maybe this number is wrong. It's okay. It's fine. Just enter any number, and we will see how to know the exact number for the original oil in place. So if you want to make it say 200, it's also fine. Use any number, doesn't matter. The start of production date, let's say that we have the production day 1/1/2017. Okay. If you check the monitor contacts button, it will need the pore volume versus depth, and it will need the rock compression in order to know the contacts between the oil and gas, between the oil and water. Most of the engineers doesn't use monitor contacts, but if you have some information about the pore volume versus depth, you could monitor the contacts in order to get better results. Okay, let's say that we have the water influx model. Until now, there are lots of water influx models, but until now we don't know whether the reservoir that we have has the a water drive mechanism or not. So we will say that it doesn't has water drive until now. The rock compressibility, we have several things to calculate for the rock compressibility. The first thing is that we enter the rock compressibility is calculated from the correlation within the software. It will calculate it manually, automatically. Second thing is that you have a variable rock compressibility versus pressure, and these are from the core analysis data. You may have this information, so you would enter it. You may use user specified rock compressibility, let's say 3.5 multiplied 10 power -6 or whatever, and you can ignore the rock compressibility. But I don't like to ignore the rock compressibility, because in undersaturated reservoirs specifically, it is very important to know the rock compressibility, because this is the main driving mechanism in the undersaturated reservoirs. So you can't just ignore it. We will select that the software will calculate it from the correlation. Okay, once we choose rock compaction. By the way, if you have the panels that have the red font, this means that you haven't filled in this panel yet. You need to fill the relative permeability, and you need to fill the production history. Anyway, at the rock compaction, if you have the rock compaction details, tank pressure versus the compaction factor, you just have to enable the model and enter it. The compaction at the initial reservoir pressure must be equal to 1, as mentioned, and then it decreases. Anyway, we don't have information about rock compaction, so we won't enable the model. Pore volume versus depth is only available when you select the monitor contacts, as we saw it before. The relative permeability data that we have, you could either enter the relative permeability data by queries functions or by tables. Water saturation versus relative water permeability, oil saturation versus relative oil permeability, and gas saturation versus relative gas permeability. But with the data we have here is a query function. Please enter these values for the example that we have: 0.15, 0.8, 0.903054, PRO 0.15, 0.730376, 1.63454, KRG 0.02 for the residual saturation, endpoint is 0.9, and the exponent is 1. Some of you would ask me, why did I enter the KRG while I don't know if there is a gas or not? Let's say that this is a default number, or this is the default value. You may get it right or wrong. It doesn't matter as long as you don't you didn't find out yet that there is a gas cap or not. So you may enter any number at KRG until you find that this reservoir has a gas cap or not. Okay, this is the water sweep efficiency if you want to change it. This is the gas sweep efficiency if you want to know it, and the hysteresis is okay. Let me tell you that the hysteresis is the normal model assumes that the relative permeability curve follows the same path when the saturation increases as it does when the saturation decreases. This is a normal model. But if you select the hysteresis to yes, or if the hysteresis option is activated, then a different relative permeability curve will be used as the saturation drops. When the saturation drops, it will goes to the normal curve we enter begins at S equal residual saturation, where KRO equals 0, and rises to KR equal KR max. Okay, when S equal S max. If we had no hysteresis, then the KR would follow the same path when the saturation starts to fall. However, if the hysteresis is right or is activated, as before, when the saturation starts to rise, it follows the normal curve from SR to S max. Now, if the saturation drops from S max, it will follow a different path. The curve will goes to another value rather than the SR or the SR max. Okay. Anyway, it's not very important to do it, but this is what hysteresis say. Okay. The last thing is the production history that we have. Actually, the production history, there is a lot of data to know about it. We have the time, the reservoir pressure, NP or cumulative oil produced, cumulative gas produced, GP, cumulative water produced, WP, cumulative gas injection if you have a water injection or gas injection. So there are a lot of data actually to know about it, but I will provide a link for the production history that we have in the links below this video. We will have all of these results, and we will say that we'll copy and then paste the table. Okay, and let's change the start production at 1/1/2001 rather than 2017. Okay, once we have filled all of these panels, we click on done. What is next? Okay, once we have finished the input of the tank data, I just forget something. In the tank data, the initial reservoir pressure is 4,000, not 2,200. 2,200 is the bubble point pressure. Okay, and let me comment on something here. If you have an undersaturated reservoir, it's fine to enter the initial pressure at itself. If you have a saturated reservoir and the bubble point, let's say that in this example it's 2,200, and now we are at the pressure of 2,000 only. Should we write 2200 as the initial pressure, or 2000 only. We will use the 2200 initial pressure if this reservoir is saturated. The bubble point, in the case of saturated reservoir, the bubble point pressure is written as the initial pressure. But here it is under saturated reservoir, so the initial pressure is 4000. Okay, so please change it. Once we have finished all of this data in tank data, we click on the history matching, where you know about whether the reservoir is water drive mechanism, a gas cap, under saturated, saturated, what is the initial oil in place, and all of this information is only known from the history matching panel. If you click on all, you will see several plots. The first one is the energy plot. This is the fluid expansion in blue, and this is the Bv compressibility, or the compressibility of the bulk volume, in green. So we will know that this reservoir is driven mostly by the fluid expansion and a little bit less by the bulk volume compressibility. Okay, the graphical method is to know, this is the old method of FWE and all of these things that we have talked about during the presentation, but this is not of interest. What is of interest is the analytical method. This blue line represents the model that you are using, and these dots, or this X, represents the production history data that you have. In order to know that the model that you have used is the same as the production history data, each one of these should match together, should coincide together, coincide on each other. Okay, how to do it? The model without water is appears as a blue line, while the model with water drive mechanism appears as red line, as we will see afterwards. So if we have the variation or a gap, we press on the regression. What is regression? Regression means that you are not sure of some parameters, like for example the oil in place. We have set it at 200 mmStB, right? And we are not sure of it because we don't know. In the regression phase, when we press calculate, the program calculates the oil in place, or all the parameters that you have checked, in order to give you the nearest match between the blue line and the actual line. This nearest match doesn't necessarily the same as the this is not necessarily the right model. But if you choose accept all fits and then press done, accept all fits means that you will use the values that you had, the best fit, and you said done. This is a match between the model without water and the production data from the field. Actually, we don't consider this as a perfect match. There is a variation here, okay, and there is a variation here also. So I guess that this reservoir has a water influx in it, and it may have an initial gas cap, but we should first try all the models of the water driving mechanism in order to know whether it has only a water drive mechanism or it has also a gas cap. How to change this from besides of pressing the finish, we can change it from the input tank data, the water influx that we have the model none, right? So we may choose small plot. Each model of these models will give you some parameters to fill. You don't know, of course, the aquifer volume, right? We will enter it as 1500 mmf T power 3, and we will say done. As I told you before, the blue line is for the one with the aquifer influx. The red line is without the aquifer influx. So we should make some regression in order to have the blue line coincide on the actual data that we have. If we press on the regression, we don't know the oil in place, we don't know the aquifer volume, but we are somehow certain of the porosity, because porosity are being calculated or are being measured at the lab. So we won't click on porosity because it's somehow very good, and we will press calculate, accept all fits to use the data that have been calculated, and then done. We will see that the red line and the blue line are coincide with each other, but not with the production data itself. So we will keep changing again. Say horse steady state, aquifer constant here, let's say it's 5 reservoir variable psi per psi, and time constant is 15 days, and then done. Then we will make regression again on the oil in place. We're not sure of it, not sure about it. Aquifer constant, aquifer time constant, and then press calculate, accept all fits, and then done. We will have the blue line here matches only at this partition, but it doesn't match here or here or there. It doesn't necessarily have a perfect match on all the production data, but at least not that bad. Okay, so we will see another water influx model. If you tried at home all of these models, let's say Horst van Verdingen deck, the system will give you a radial aquifer, linear, or bottom. If we choose linear aquifer, it will give you constant pressure or sealed boundary or infinite acting. Let's say we have a sealed boundary. The reservoir thickness is 40 from the logging data. The reservoir width is 250 feet. Aquifer volume say 2000, and the aquifer permeability, let's say let's say 5 millidarcy. Okay, and then done. We have a regression on oil in place, aquifer volume, aquifer width, reservoir thickness. We won't click on it because you are supposed to have the reservoir thickness from the logging, and it is somehow accurate. The same for the porosity, but the aquifer permeability is not accurate, so we will calculate it. Accept all fits, done. We still doesn't have a match. If you keep trying and choose Horst van Everdingen, I don't know his name actually. Anyway, the modified model, and you see the radial aquifer with a radius of 150 feet, outer and inner radius say 20. The encroachment angle, the aquifer permeability say 10 millidarcy, and you press done. And then in the regression, you don't know the oil in place, the outer and inner radius, you don't know about it, the radius, the reservoir radius, you don't know about it. Encroachment angle, I'm not sure. Reservoir thickness, porosity, and the aquifer permeability. Okay, let's calculate it. It will take a little bit time because you have a huge number of iteration and standard deviations. So once it is done, accept all fits and press done. You will have a nearly perfect match here. You see? All the way you nearly have a perfect match. But does that mean that the model that you are using is the right model? No, it doesn't necessarily be the right model. Why? Let's look at the calculated oil production data here. You have the tank pressure, the porosity, the connect water, and so on. The aquifer model you are using, the outer and the inner radius 27.5, this is a reasonable value. The encroachment angle is nearly 360, a reasonable value. The calculated aquifer volume is 1 multiplied 10 power 6 mmf T power 3. This is a reasonable value. And so for the aquifer permeability, 23 millidarcy, tank thickness 129 feet, and the tank radius 490. This is a reasonable values for the aquifer. But let's say that we have used another model and give you a perfect match just like this, but you have the porosity, if you have ticked on the porosity, 0.032, the porosity is 0.0032. Is this a reasonable value? No, it is not. You should not only depend on the matching between the aquifer model, the aquifer influx model, and the production history. You should count on the matching besides the data that you have. Okay. Anyway, we will suppose that this is the right model that we are going to use. How can we make sure that this is the right model? Let's press on finish. Come again to history matching, and then we run a simulation in order to know if this model is right or wrong. We press calculate. This is the calculation of the simulation according to the model that you have entered. And then you press done. Why did we do this? I will tell you later why. After the history matching, you will press on the FW matching and FG matching. It is the fractional water flow and the fractional gas flow. This is useful only if you have water injection, or to know the water breakthrough and the gas injection and the gas breakthrough and so on. You can press also regression on default variables. It won't give you an accurate because we have so little data about it. It is supposed to have the S-shaped curve, as you all know. So it doesn't matter now because we won't have a water injection case in this case. Just finish. If you want to save the regression, say yes. Say yes. If you don't, say no. Okay. Anyway, the production prediction is the last thing that you would need to know after the history matching. You should pay attention that after the history matching, we know that the reservoir has a water influx and oil, right? As I told you at the beginning of the video, the oil the oil is represented by the green color, and the water is represented by the blue color. Okay. At the production prediction we press on the prediction setup. You have three options to predict. Either to predict the profile from the production schedule, no wells, or the tank. This is when you have only tanks, the data from the tank only, or the reservoir only, not from wells. Second thing is that you predict the production profile using the well models, if you have the well models and the IBR and the VLB and so on. Or if you want to calculate the number of wells to achieve a certain target rate. Let's say that you have 5 wells producing Q equal say 500 barrel per day, okay? And you want to increase this target to 700. MBal has the availability to calculate the number of wells to achieve this target. Anyway, we will choose here as a predict profile from production schedule, no wells. If you want to have a water injection or not, if you want to have a gas injection or not, and the gas recycling and all of these things. The prediction setup size is whether you have you want the prediction after every 15 days or automatic. If you want user defined 15, 20, 30, anything, but we will keep it automatic. In order to know that the model you have done is right or wrong, we should make the prediction start at the start of production and ends at the end of production history. Why is that? I will tell you later. And then press done. Then press production prediction again, and then production and constraints. Production and constraints means that you have, if you have the actual data of the production and prediction, it's okay to use it, of course. The time, the average oil rate, the average gas, and so on. If you don't, you can copy it from the simulation data that you have already done. He will tell you that this option resets the current data and copies across the simulation data. It will take the average oil from the simulation data according to your model, and we will say yes, okay, and then done. The last thing is the reporting schedule. Do you want the reporting schedule, say every month, every year, every 2 months, every 2 years, say we want it every 6 months. You will write down 6 and choose months, okay, and then done. Then you run the prediction. Press calculate. It gave you calculation because until the 1st of July 2006. Why is that? Because we said that the production prediction will start from the start of production and ends at the end of production, right? If you clicked on the plot, you will see the time versus tank pressure, but we want to know all of the data, the tank pressure versus time and the cumulative oil versus time also. This is for the simulation data, this is for the prediction data, and this is for the production or the actual field data. From variables, we will select the prediction, the simulation, and the history. Okay, this software gives you the flexibility to choose 2 things, not only one, tank pressure, and the second is the cumulative oil production versus time. If you want to change this, you may click on tank pressure and one solution gas oil ratio and so on, okay, and then press done. If you look here, you will find a perfect match between the history and simulation and prediction as a cumulative oil. All the 3 lines are coincide on each other. But if you look at the production prediction, if you look at the tank pressure, you will see that the history and simulation data are just coincide with each other, or a good results at least, but the prediction is away from them. This huge difference between them means that if you use the model that we were talking about, you would probably have wrong results at the actual data. If you predict the future data after, say, from 2006 to 2012, you will have another results, and you will get lost and you will get confused. So this means that the model that we have used is terribly wrong. Okay, we press done. We may change the production and constraints to these values, and I will provide you with a file of these values. These values are the actual data that we had from the field, and then we press done. If you copied these values from the simulation model, you would probably have a new different prediction model and you will get lost. But if you enter the actual field data of the average rate, oil rate, and the maximum liquid rate and the maximum water rate, you would find the perfect match. Once you enter these data that I will provide you with it, select done. Sorry, it's okay, and then run prediction, and then calculate again using the prediction until he said that the pressure has dropped to 0. It's okay. We are fine with that. Once you plot the data, you would have you would see that the cumulative oil production here. I'm sorry. The history and simulation lines are coincide with each other besides the prediction as we saw it before. But at the tank pressure, the tank pressure history, the tank pressure simulation, the tank pressure from the prediction, all of these things are coincide with each other. So this is a perfect match, and this will give you the desired prediction that you always seek for. Okay. If you want, the last thing that I will say during this session, if you want to give a report or know, beside, if you have all of these data, right? The oil formation volume factors, the Bvt, all of these things. You want to save all of these things. What can you do? You choose report, and then report to a file, and then report again, and you write down the name of the file you want, like SPE. It will be saved as a text. Okay, and then you press done, and that's it. So unfortunately, this is the end of our session, guys. I hope you like it, and I hope that I have provided you with all the information you need to use MBal software. Let me remind you that you have my email. If you have any inquiries at any time, you can send me and I will welcome it. Good luck, guys, and I hope you enjoyed it again. Bye.